sessions. However, the excursion around Korea National Park is planned in this afternoon. Now, let's concentrate in these 3 hours morning sessions. As you are informed, the original plan program was little changed. In the material science studies session, there are 6 presentations. Dr. Skaranutsi and I, Asami, co-chaired in this session. And the first presentation is number 032, excuse me. And the name of the presentation is Progress Report on the research activities on cold fusion at NAR plus 15. Presented by Scaramuzzi, Beltarot, De Marco, De Nino, Rattorio, Labera, and Violante. The presenter is Dr. Violante, please.
Good morning, ladies and gentlemen. This is the report of our activity about cold fusion in Frascati. And our activity is developing basically on 4 points: calorimetry, material science, theory and modeling, and even for measurement. Even if the last point is still in progress. Just with a short resume of the calorimetry, let me show you our calorimetric system, which is being done by cells contained in viewers and operating inside a thermostated box. We use flux calorimetry, and here there is a short, simplified view of our cell, where the heat is removed by means of a pipe, where is circulating cooling water. Anode and cathode are in the middle of the cell. This one is the white signal for our cell when we have 5 bars of input. As you can see, for 5 bars, the error is ranging between plus and minus 50 millivolts. We have also done a finite element analysis of our system just to have a map of the temperature inside the cells when we are operating at different power. And the accordance between the theoretical calculation and the measurement are satisfactory. In this table, I reported the main results concerning our calorimetry. As you can see, showing the reflection. Okay, sorry. Yes, as you can see, we used different types of palladium, coils and wires. And the excess of it is ranging between 1000% to less than 10%. And the waiting time for the excess of it is ranging between several weeks and few hours. What we discovered is that between these coils from one batch and this other one from another batch, there is a substantial difference because we checked the solubility of hydrogen in this batch, and we discovered that the solubility is much higher than in this one. And we correlated this effect with the microstructure of the metal, which in this case was very different. Then we decided to start with study of material science to understand what is the real inhibition inside the material for having high loading ratios. So we decided to interrupt for some time the calorimetric measurements and to start with loading study. For more than 1 year, we have been working with hydrogen instead of deuterium, I mean with light water, for obviously economical reasons. And before going on, let me summarize some points. We know that the entrance of hydrogen in palladium is conditioned by a thermodynamic equilibrium between the chemical potential outside the cathode and the chemical potential in the solute inside the cathode. And the chemical potential inside the cathode is modified by all of the force field that modify the free energy of the system, as has been well explained in the excellent paper presented by Professor Oriani in the Mallove conference. We know that the chemical potential, when there are stress fields, which is a force field which modifies the free energy, is modified in the sense that we have an additional term plus the chemical potential when stress are not present in the medium. And this is a problem of equilibrium, strongly related with the not equilibrium problem concerning with the mass transfer. The flux equation in presence of stress modifies according to the following law, which reduces to the peak law when the stress gradient is 0. It's very simple to demonstrate that the flux is 0, can be 0, even if the gradient of concentration is very strong. But the condition is that this term must be equal to the second one in the brackets. From simple calculation, we see that the difference in local stress in the medium is in the order of the stress produced close to a dislocation. Then we can imagine that when we are loading hydrogen, there are produced stress able to stop the flux even if the concentration gradient is very strong. Then stress are produced at the beginning, loading, in the coexistence region of alpha and beta phase, because beta phase is growing up inside the alpha phase, and the difference in the lattice parameters is very significant. And then we have mismatch at the border zone. And this is a case of coherent stress, and when the system is rearranged, we have a not coherent stress, and in reality the situation is in the midway between. Anyway, to avoid this coexistence of stress, we prefer to load following this pathway. So we heat the system up to 350 centigrades with the pressure which is about 30 atmospheres, and then we wait for a time long enough to move the concentration inside the medium above the beta minimum value. In this way, we obtained, first of all, different macroscopic behavior of the medium material after loading. As you can see, the yield stress for cold worked material loaded up to 0.7 is 275 megapascal. When we heat the system at 1000 centigrade and after we load at 0.7, the yield stress is 148. This value are the average of medium measurements. And when we heat up to 1000 centigrade and we make the pre-charge in gas as I showed you before, the yield stress reduces to 100 about. So there is a macroscopic difference. In terms of loading, we have this behavior. Here we loaded a cathode, which is a membrane foil of 0.15 millimeters thickness. And we see that if we start from zero concentration, with electrolysis, the system asymptoticizes to 0.7. Instead, if we start from a preloaded system with gas, applying the electrolysis, we arrive up to 0.9. So, but this is not enough to go close to 1 as required by reproducibility of cold fusion effect, as well studied by Dr. Pulinazzo and Michael McCougan. Let me sketch the situation. We have a medium where the hydrogen is coming in this side, then we have a concentration profile in the bulk, and there is a zone where the concentration of hydrogen is higher than in the other one. Then here the expansion of the lattice is larger than there. So by applying the elastic equilibrium theory, we can see that this zone is maintained, compressed by this other one. Then the chemical potential of the hydrogen inside this region increases. And what can happen is a stop in the evolution of the loading, of course. Then we have to start something to go over this condition. This is a simple qualitative analysis which takes into account the mass transfer across the grain and across the boundary of grain. Of course, this is an ideal analysis, considering no defect in the grain boundaries, and by solving this system of differential equation, one for the grain, the other one for the boundary, we have these results. If the grain boundary, I mean the pathway for hydrogen, is very narrow, we have the creation of steep gradients inside the grain. Then we can suppose that here there are significant stress in the grain. In the case of enoughly large boundary, we have flat concentration profile after the same time. So the stress are reduced. Of course, if we consider system where the diffusion coefficients in the boundary grains are different, the situation is perfectly equivalent, even if the dimension of the boundary is the same. Then we try to modify the material, but first to go on, let me show you some other analysis, semi-qualitative if you like. We have now to introduce the stress effect in the mass transfer equation. So we know that the stress, local stress, is well related with the strain by means of the Young module, and we know that for the beta phase, the strain is correlated to the concentration by means of the following relationship. Then, by the substitution in mass transfer equation, we obtained this nonlinear distributed parameters differential equation, where these terms 1 minus eta appears from the terms containing the stress effect. And you can see that eta is the percent of relaxed stresses. Then when eta is 100%, the diffusion is the Fickian one. Let's go in the simulation, and we can see that if the stresses are relaxed enoughly, the evolution is quite similar to a diffusion, Fickian diffusion. So the system asymptotizes to a loading 1-to-1. But if at some instant, some moment, the percent of stress, or relaxed stress, reduces, we see that the asymptotic behavior changes dramatically. And if the reduction is a little bit more, we see that we can have a spontaneous deloading of the cathode until the stress is relaxed again a little bit, and the concentration increases again, and then it can go down, as we observed that experimentally, so this fluctuation. In our study, we try to modify the metallurgical status of the metal. This is a cold-worked palladium foil, where we performed the lamination starting from 0.7 millimeter thick foil until 0.15 millimeter of thickness. And we see a very large concentration of defect, of course, in medium. Then, after heating for 1 hour at 900 centigrades, we have this arrangement of the materials with this location arrays. And if we anneal mode, we see that the lattice rearranges with the nucleation of grains again. And then we suppose it to have a different loading condition in such materials. Then the results are summarized in this sheet. As you can see, the best behavior is done by cold working plus annealing at 900 centigrade for 1 hour. The behavior of the cold worked metal is this one. This, of course, can be maybe improved as measurement because of some problem in the measurement of the loading ratio by resistance evaluation. But in any case, the behavior is indicative of a different loading evolution in the movement. Then, starting, finish. How long? 1 minute? 2 minutes. Okay, thank you. Here, there is the effect of the dynamic loading in the final equilibrium value, and we see that we have a strong effect of the high-low status of currents, because in working in low status, we have a reduction of the concentration, and applying high current, we have an increasing of the concentration. So we produce basically this effect in the medium. So we start from a situation like this with a very deep, very strong concentration gradient at the external side, and then we have strong stress here that can be reduced by applying the Tagarashi technique. Then, at the end, we decided, just a little bit more than 1 month ago, to start again with calorimetry. And these are the results. So, with low currents, we obtained a very high loading ratio with deuterium, and no excess of it. By increasing the current, we obtain the excess of it well above the sensitivity of our system for 2 watt of input, as in this case, with a very high loading ratio. By increasing the currents, the excess of it increases again. By switching off reducing the power, the electric power applied to the cell, the excess of it disappears, and appears again when we increase the current again. Then we started the system with an addition of electrolytes, and the excess of it disappears. And this excess of it is also well located in the well-known storm tubes here. The red points at this point are other experiments that we have performed in Frascati. Thank you for attention.
Please.
First of all, Vittorio, that's a wonderful paper. I congratulate you on very useful work.
Thank you.
Let me introduce another factor though. When you go through the high-low cycling process, you also have the possibility of depositing species on the surface, excuse me, which affect the absorption. I did a model of the Takahashi cycle in the presence of lithium in the electrolyte. And what happens probably is, at the very high current levels, you deposit lithium, which impedes the ingress of deuterium. You go to the lower current level, the lithium leaves the surface, leaving the surface free to absorb. So the stress thing is clearly important and produces, I think, the results that you described, but also the absorption, desorption of species from the electrolyte will produce similar effects.
Thank you, Mark. Actually, your interesting point. I had not the possibility to say that there are many electrochemical problems accompanying this material problem, because I have not enough time. For instance, just to repeat what you are telling now, this is the effect, very funny effect, of the solution aging on the loading. If we prepare the solution and we store the solution in a glass bottle, we have a chemical attach of the bottle, and then we have many impurities in the solution. And then we discovered that the optimum is after 1 month. Anyway, so I know that there are very important electrochemical problems that are not easy to control. Thank you.
Is there any other discussion?
Excuse me.
Next, please.
Do you have any information?
Excuse me. Next, next. Very short.
Any information on Christmas?
Thank you very much for your excellent result for us. And I would like to know about, you mentioned about, at first, locally stress occurs, and after that, you said to me, relaxation occurs. At that time, you mean that this generation of dislocation or motion, and do you count such kind of dislocation motion or generation effect for the diffusion of deuterium?
Well, what is our feeling is that if we have oriented dislocation, maybe they help the material to relax the stress. But you know that when you introduce hydrogen, there is a formation of dislocation, random formation of dislocation, and this formation produce crossed dislocation that can reduce the ability of the material to relax the stress. In terms of help for the mass transfer, probably the effect is negligible, but this is just a feeling. A lot of work is required on this field if we want to know everything. Thank you.
Okay, thank you. Next, please.
Excuse me for interrupting the floor. Do you have any information about following this 900-degree annealing, what sort of a range of crystal sizes you have in the
Range of?
Crystal sizes?
Well, this is 200 nanometers. 200.
200 nanometers.
Okay.
Thank you.
Thank you, Dr. Sanchez. Sorry. Now the time, next presentation. Number 24. Number 24, the cycling of negative emissions induced by electrical currents and phase transitions in tightly deuterated films presented by Sanchez, Tebas, and Fernandez. The presenter is Dr. Sanchez, please.
Thank you very much. Good morning, everybody. The title of the presentation is, you know. So you can see that we are still interested in looking for neutrons. We are confident that it's not easy. There are not many neutrons, but we think that it's still important to try to have a confirmation of the existence of neutrons emissions in coefficient experiments. We are particularly interested in 2 points at the moment. First, see or try to relate the quality of the material with the nuclear phenomena. And the second one, try to see or to investigate in some stimulation or triggering mechanisms for neutron emissions. So, in the presentation, I will follow the summary. I will leave previous works for the end of the presentation. I have time enough, so I will try to speak about preparation and properties of the metal matrix we have used. This is titanium produced by the titanium iodide method. Second, I will say a few words about hydrogen characteristics of this type of samples. And finally, I will speak about nuclear reaction in solids, experimental results, by using 2 different stimulation techniques, electrical currents and phase transitions. A few words about the material. This is the glass bottle where the material is produced. Titanium is deposited in hot tungsten filament by starting with the titanium tetraiodide. The tetraiodide is decomposed in the hot tungsten filament and is deposited there. The glass bottle is after closed vacuum, and there is in principle no air contamination of the titanium produced. So the same bottle is used in our cold fusion experiments. This is this way, perhaps. This is a cross-section view of the material. The clear line in the middle is the tungsten substrate, and around it is the titanium deposited. The thickness, you can see perhaps the scale here, the thickness of the material of the layer is about 200 microns. The the width is about 4 millimeters, and the total length is about 4 centimeters. The material obtained was analyzed from the point of view of the gas impurities content and also from the point of view of the metal impurities content. This is a result by using OEA electron spectroscopy. Our sample R21-1911, and this is a commercial sample, high purity commercial available sample for comparison purposes. The best result is that we have a very low contamination with carbon, nitrogen, and oxygen. You can see here, for example, in the case of the sample we use for our cold fusion experiments, we have carbon, nitrogen, and oxygen on the other or less than 2% atomic contamination. The mass of the titanium in all cases is around 50 milligrams. We didn't find any metal contamination except that coming from the substrate. There is a diffusion of the tungsten into the titanium, and these are some profiles. This is the titanium profile, and this is the tungsten profile. You can see here the cross sections. This is the tungsten, this is the titanium. If sun alloy is produced, alloy titanium tungsten, you can see here, this is the tungsten, this is the alloy ring, and this is the titanium ring. So we finally growth the titanium by putting a low tungsten temperature in order to avoid the tungsten diffusion into the titanium. The tungsten has a negative influence in the high transmission characteristics of the titanium. This is a proof of that. You can see here two sample growth bias and one commercial sample. The commercial sample has no tungsten, so you can see that the PXT curve shows no hysteresis and a high loading. However, our samples with contamination of tungsten has a high hysteresis and a more difficult loading at high pressures. So, as I said, the sample we use finally for cold fusion experiments were produced with low tungsten temperature, so no tungsten contamination. This is the experimental installation in our cold fusion or nuclear experiments. We have here at the bottom of the sample, we have two nuclear detectors. One is NE213, the other one is PC500. This is a scheme of experimental installation. We have mainly two parts. This is the sample voltage. One electrical part to control the current intensity going through the sample, the voltage drop, the delta pressure and the temperature of the bottle. And the other part is related to the nuclear detectors and the electronic. We are able to detect in time and energy. These are some patterns of the electrical current we have tried for stimulation or trying to trigger some nuclear reactions. We sometimes use continuous high current, this is intensity, changing the value or different wave shapes, as you can see. The second type of experiments we have done is trying to see if phase changes in the sample are acting as triggering or stimulation processes. We have followed the phase changing by measuring the electrical resistance of the sample in situ during the process. This is an sample of the electrical resistance variation on passing from the beta to the delta phases. There is, as you can see, some hysteresis in the process. This is due mainly to the production of defects, dislocation, and small cracks. These are some results. Excuse me.
Yeah.
Anyway. These are results of the experiments. If we follow the current pattern, here are the counts detected in real time during the experiments in one detector and the other. So, after doing this, we finally analyze the results by taking different integration times in the experiments. Firstly, let me say a few words about the background we have. These are the data about the background, one detector and the other. We are able, by doing different integration times, we are able to detect, this is the minimum value we are able to detect, 200 for example, by 20-second integration time, we are able to detect 220 neutrons per second coming from the sample. This means in our detector 3 counts in 20 seconds. This is a significant signal from our home. This is obtained by adjusting the background counts to a Poisson in short times and to a Gaussian in long times. The significant value of counts detected in the integration time is coming from this point higher than this or higher than this. For example, in the BC500 detector, if we use 20 seconds, integration time, the significant counting level should be 15 counts. If we use 1,200 seconds, the significant counting level will be around 370. These are some data, the real experiments. This is the number of the experiment, 1, 2, 5, and we can see the data, one detector, the other detector, and the only significant events we have detected are 3 counts once only, 3 counts once only in one detector, in the other 16 twice, 15 one, which are significant. But unfortunately, there is no time correlation between the signals coming from the 2 detectors. This is a real problem. By using a different integration time, longer, 1,200 seconds. These are, for example, the experimental result. These are the background level, and this is 3 sigma of the background level. This is the value we consider significant. We have all the experimental points within the background, except some events like this or like this, but there is no, I said before, these are in both cases from the same detector, correspond to this experiment and to this. The signal are significant, I mean, about background. This corresponds to 5 sigma, this other to 4 sigma, but in the other detector, the NE215, there was no correlation, no sign correlated to this one. And by using the whole experimental or the whole experimental time, I mean the total of the time of the experiment, we have this analysis, and these are the data. You can see here the data from the experiment, the background, and there is no significant deviation of the signal from the background. There is some curious fact. You can see that all the signals in the experiment are a little bit higher than the background signal, but within the 3 sigma deviation of the background. Let me show this. This is the state of the sample, I mean the titanium foil. This is before the experiment. This is after the experiment. Highly deformed, distorted. There is the sample deformed more or less 20% in length, extraordinarily deformed, as you can see. And so I would like to conclude. This is, we can say that we have in these experiments no clear evidence of the presence of nuclear reaction in the solid, at least from the point of view of the Newton's production. So about the minimum level we are able to detect, which correspond to 10 to minus 21 fusion reactions per pair of deuterons and per second. And also we have detected some anomalous events, mainly related to the moments where high current intensities are passing through the sample, but without correlation, time correlation between the 2 detectors. Anyway, we have the feeling that this type of experiments must be reproduced or try to repeat. So we have the purpose of trying to follow this line and make another experiments in this context. I would like anyway to make a final comment. First, we have a very small mass of titanium, I said around 50 milligrams. This is a problem, I think, from the point of view of the intensity of any possible signal. And secondly, in the deliberation process, we were able to confirm that we have a deuterium to titanium loading ratio higher than 1.6. But we are not able for the moment to say, we are not able to say, thank you, how much suddenly we have. We can say that higher than 1.6, but we don't know exactly how much. We, in a recent paper we have published, we have shown that probably to have nuclear phenomenon in titanium, a loading ratio of the titanium ratio of the order 1.95 is necessary. So if this is true, we are not. We might be under this loading, critical loading ratio. That's all. Thank you very much.
It seems that in the titanium system, there are very different conditions depending upon the temperature ranges that are used.
Sorry, I don't
depending upon the temperature ranges that are used, there seem to be very different situations. Early on, Howard Menlo pointed out that it was really in the limits of sort of like no loading, but that was at low temperature, where you would see the phenomenon. And my question is, where were the temperature ranges where you looked at things, and have you considered, are you capable of doing the very low temperature type situations and monitoring effects going through phase transition? I mean, the loading, I think, nobody before has the capability, the excellent capability in studying the system to really monitor loading and phenomena. Thank you.
Okay. Well, when we were growing in the lifetime, we were able to know exactly the growing temperature by using optical detectors of the radiation emission. But during the nuclear experiments, we were not able of measuring exactly the filament temperature. The only thing we were able to do was to see how was the temperature in the bottle, the bottle water. So we have an idea, we have no exact data of the temperature of the sample. But several of the experiments, we pass it through the sample currents of the order of 13 amps. It's very high. So we saw clearly, in some cases, how the sample was bright, white bright. It means maybe around 1,000 degrees around that. And in another experiment, we cooled down the sample to liquid nitrogen, and after, so the sample temperature might be a little bit higher than liquid nitrogen, in fact. And after that, we heated the sample for this low temperature to around 1,000 degrees. This is continuous. So we cannot give exact data on the temperature of the sample, but we are completely sure that we change it very periodically, the sample temperature from very low to very high temperatures. And in these cases, the deuterium from the sample is absorbed and dissolved, because all the experiments were done with deuterium atmosphere within the water. So on heating and cooling, deuterium is absorbed and dissolved. And this is another critical process to try to see if there's any stimulation.
Right. I mean, I think the point is this is a very delicate system, and you have tremendous capability to really explore it. There are a lot of parameters involved.
Yeah.
In the early, I mean, if you build on what was done earlier, low temperature coherent effects seem to have been very important at very low loadings. Now you have the capability to potentially start from there and to go to higher and to really explore that. I mean, I would encourage you to try, if you can, to really explore the lower temperatures and to try to make contact with them.
Yeah, the main point we try to see is we have the impression by using different titanium coming from different suppliers. We had the impression with our data that characteristic materials are very, very different depending on the supplier. No? So finally, we conclude that perhaps it would be convenient to try to grow the materials in order to control the purity and the crystallographic conditions. So, for example, here we are using titanium with a grain size which can be controlled by cooling the sample very, very slowly once the sample is already growth. And we have a grain size of higher than 20 microns, but very reproducible anyway. And the purity is quite good, as you have seen. So our focus was mainly try to have well-controlled materials and to see some experiments. We have the purpose to continue and make a new experiment on this line, always with the material brought by ourselves and try to see what happens.
One more question. Okay, please.
Just a short question. In the case of anomalous events you measure on neutrons, did you check the path shape of your signal? The path shape of your signal. The path shape when you detect neutrons.
No, well, you know that our criteria before doing the experiments were the following. First, if we see a signal, we are confident, first, if both detectors give correlated signals. This is the first criteria. The second one is if the signal is related to any stimulation we do to the sample. I mean, it's not erratic. So we try to correlate different stimulation of the sample with the signals. If we don't see any relation of the signal with the stimulation, we are not very confident. This is the first criteria. So we didn't see that actually.
But never you check at the oscilloscope the shape of the signal, because in some cases there are some peak-outs. So you can have that one detector take the peak-out and the other not. So the proof that you have a true signal coming from neutrons is to check the path shape.
We tried many times with the oscilloscope, but during the background, when we were taking backgrounds, we analyzed the signal with the oscilloscope to see this today. When making the experiment, not exactly.
Thank you very much. Presentation number 26. Parameters affecting the loading of hydrogen isotopes into palladium cathodes. Presented by Tanzera, Crutchbaker, April, and Makoeto. Presenter is Dr. Tanzera. Please.
Thank you, Mr. Chair. I'd like to simply take the next 15 minutes, bring you up to date on some of the non-calorimetric experiments we've been doing in the last 18 months. Take this opportunity to acknowledge the support and collaborative efforts of NETO, IAE, and the New Hydrogen Sapporo Lab. I'd also like to thank the IMRA Materials Lab and the IMRA Japan Lab for supplying some of the palladium, which I'm going to speak today. Outline of the talk, so broken into two parts. I'll bring you up to date on some of the results of our degree of loading experiments, examining some of the materials parameters and some of the additives, the electrolyte, electrochemical parameters, and then also some palladium surface potential measurements that we've been doing that hopefully can tell us something about a better way to understand loading or understand the surface loading and see how that relates to the bulk loading. And also with the reports, particularly one you heard this week from Ed Storms, using an open circuit potential to predict excess power. Also to try and understand how we can do that in situ in our system. The background, you've seen this before, our 3 criteria for achieving excess power. We want to first achieve that in our degree of loading cells. We need high DPD loading. We need that high loading at high currents or current densities. And we need to achieve both of those for extended periods of time. In order to achieve that, there are many things that need to be controlled. I've listed a few and then simply mentioned there are other, many not yet identified parameters. And that affects the replicability of certain experiments. And then those reports I mentioned also earlier in the field, I remember Martin Fleischman claiming that measuring that cell potential or surface potential can be a useful predictor in good loading or excess power. Check. Well, as you may have noticed, in the past few years, we haven't reported the same amount of excess power results that we had early on. And so we've re-examined what did we do earlier and what can we learn from it and try to reproduce it. So I've listed our standard procedure that we've used in our earlier successes. But also, one of the things we did change over the last few years was the size and shape of our cell, and that affected the anode-cathode configuration, which affects your field lines and the efficiency of your current density and the homogeneity of your current fields on the cathode, which is going to affect your loading. And so we've gone back to a new cell design for our degree of loading and our calorimetric experiments, and we try to go back and reproduce what we consider to be the optimized anode-cathode configuration. And I won't go over the other parameters, we've discussed them many times before. Our degree of loading, we call it a farm concept, but what we do is we take the same cell that we're using in our calorimeter and put it in a set of benchtop experiments and use maybe 6 or 8 of them, and then put in a number of experiments, usually identical. Sometimes we'll run a matrix of different types of parameters, and then allow them to run for a while. And when we think we've got a couple that have loaded to a high enough state, we'll transfer them from that benchtop experiment into the calorimeter. Many times in the past, we used to actually take the cathode out of the cell and transfer it in air, manipulate it, and re-spot weld wires and put that into the calorimeter. And sometimes it worked, but most of the time it didn't. And so we decided to redo the concept so that we have a cell that we can just pick up, move over, and put in our calorimeter. In order to do that, we went back to our earlier electrode chamber design, the anode-cathode configuration. So it allows for that transfer. In order to do that, we do need an open circuit. So I'm going to spend some time determining what, if any, negative effects there might be of opening the circuit and taking the cell and moving over to the calorimeter. It takes us minimum 30 to 60 minutes to perform that operation. And of course, we're going to go into our closed, thermodynamically closed calorimeter, the test cell. We have a recombiner in it. And so we have to test our benchtop experiments with recombiner. And then we have automated repeating current protocol, just keep on stepping the current through different levels in the benchtop experiments, and then change that anywhere between a 48 and 96-hour cycle. And that should yield the best loaded cathodes on the bench. Then we can test the effect of high current density and test the temporal reproducibility of cathodes loading, since it goes through the same cycle 10 or 20 times over the length of that experiment. Well, let's take a look at some of the results. This is a results of a piece of palladium received from Member Materials. This one was cast in a vacuum from high purity palladium powder with no additives in the casting. And as you can see, it's a very facile loader. It deloads rather quickly and then loads to a very high state at quite low current densities. And down here, this resistance ratio on this scale versus time, and this resistance ratio on this very dark dotted line is 0.95 or higher. But that's about 200 milliamps per centimeter squared. As we proceed, even only slightly higher current densities, we're deloading up to, this is probably about 0.9 or less. And in our criterion, we feel that's borderline. We'd like to be above 0.95 down here and hopefully maintain it, or at least be near 0.95 at 300 to 500 milliamps per centimeter squared. This is an example of our current step cycle. You can see this current versus time current on this scale. So we just step that up. This is a 96-hour cycle. We'll just go from 50 milliamp per centimeter squared to 1 milliamp per centimeter squared, back down, start all over again. As I mentioned, we have to, of course, perform that open circuit time when we move from the benchtop farm to the calorimeter. And so we perform this experiment, take a look at what the effect of open circuit is. I don't want you to get into the details. It is a busy slide. So, see, this one here is a similar step cycle, about 48 hours, the one I just described, but I've inserted a 5-hour open circuit. And we do that, and we get about a loading of 0.9. When I add a 30-minute anodic strip to that 5-hour open circuit, then we actually load down here only about 0.93 in this particular material. This is a 3 millimeter cathode from Engelhard, which we've machined 30 millimeters long. And in the third one, we look at, I remove the open circuit step and only perform the anodic strip. And you can see it doesn't load quite as well. Maybe the 0.9 and 0.92, 0.91. But what this tells me is, yes, the open circuit is okay. Not only is it okay, when I combine that open circuit with the anodic strip, I actually tend to do a little better. Before you can learn something from these experiments, you have to know what your replicability is. You run 6 experiments. How well are they going to reproduce each other? And the answer is not good. I've chosen 2 parameters to determine how good these things perform, and one of them is the maximum loading and the current density of that maximum loading, and the loading at some higher current density, at least 300 milliamps per centimeter squared. On this slide, they happen to be the same number. These tend to be reasonably well performers. So you've seen 9493 at over 300 milliamps per centimeter squared. What I learned from this is I'm not going to get enough replicability to be able to do a classical matrix experiment. I'm simply going to take the best performance from here, put that on my table for future reference, and hopefully when we solve the replicability problem, that number will be used to compare to other experiments performed under different parameters. Okay, what about different palladium sources? Here's a comparison of 4 palladium sources. that we looked at is an angle hard line block 5 we just looked at, one from Mineral Materials that was cast in air with calcium boride added, another one from Mineral Materials which was cast in vacuum with no additives, and this Johnson Matthey special low platinum groove metal material. And as you can see at low current densities, these guys do pretty well, but this one in particular doesn't do well at higher current densities, but that guy does better. So that for some reason this material that was cast in air with calcium boride added seems to hold its loading somewhat better. Okay, what about some additives to the electrolyte? Here we'll talk about aluminum. And within a particular piece of palladium, in this new cell design, you go through here, you see no aluminum with aluminum, over here even worse. And all of them seem to achieve worse loading with aluminum present. I've just thrown this guy in to show you how it did in our old cell. That's pretty much a champion from some of our old cell design, but like I said, that doesn't do any good if you can't get it in the calorimeter and measure some excess power. A few other additives. Samarium and neodymium have almost no effect on loading. Doesn't make it any better. When we have aluminum and we add silicon, this has changed very little. So we had aluminum at the beginning of the experiment, added silicon. After 500 hours, no change. Had aluminum added copper, it got worse. These numbers are much worse than what we normally get with the IM number 1. And then down here on the bottom, on the hypothesis that when you have open cells that load better than closed cells, one of the reasons is something's being added every couple of days when you make up your E2O loss. That might be chloride, and so we added chloride to this. And what we actually found in this experiment is it did get better for a few cycles and then got worse again. So it has a temporary increased loading. So what we've learned there is from our degree of loading experiments is, yes, different palladium loads differently, different cells, not surprising. You can get up to what we consider an acceptable loading at low current densities, but hard to keep that very high loading at higher current densities. We can get there with the Mineral Materials material and the air cast and calcium boride palladium, and it performs better than vacuum cast. Replicability is still a problem. The anionic strip combined with an open circuit does well. Open circuit doesn't give you any problems. Aluminum and silicon have no obvious benefit. Chloride has a temporary benefit. Copper is definitely bad. Okay, I want to spend a couple of minutes before I run out just talking about surface potential measurements, and I won't go through this in detail, but that's the cell we used. And what we found is they do track the surface potential that we're measuring, does track the loading measured by resistance ratio. When it comes down here, it tracks it completely. And that was in a special cell. In our own cell, we see the same effect, surface potential at the top, tracking the bulk loading, and tells us that we can measure something that hopefully will be useful in the future. And what have we learned from some of these experiments? One, care for palladium and electrolyte preparation can yield high loadings at low current densities, not a surprise. Occasionally you can get to the good loadings at higher current densities. One material better than the other. You can make more of that or get more of that. Replicability is still remaining. Most cathodes load well using a combination open circuit. Aluminum, silicon, chlorine may be beneficial. Copper is bad. and we can get surface potentials in situ in a cell that we can put inside our calorimeter. Hopefully we can use that as a predictor of excess power in the future. Thank you.
I'm very interested in the surface potential. You actually take the electrode out and measure the surface potential in vacuum.
No, I'm sorry. Breeze through that a little bit too fast.
Yes, I really couldn't see what was on the slide.
Yeah. So no, this is in situ.
In situ, the actual cell potential you're measuring.
No. In one experiment we put together, and thank you for asking that.
I just want you to draw your attention to something in a minute.
Okay. In one experiment we've done pretty much the best you can do without using a Looking capillary. We wanted to avoid using a Looking capillary. So we put in essentially a standard hydrogen electrode and kept the oxygen away.
The matter I want to draw your attention to is there was a lot of interest in the 1930s, especially in the Soviet Union, in measuring the surface potential of membranes when the membrane had been loaded, and not just palladium but other materials as well. If you haven't seen that literature, I would commend you to have a look at it and see whether there's any parallelism you can draw between the vector chemical measurements and the actual surface potential measurements.
Okay, thank you very much.
Next, please.
You mentioned that, I gather, I mean, it was sort of hard to understand. You mentioned that the aluminum seemed to have no obvious benefit. I take it that was for loading and sustained high currents, is that correct? I mean, the aluminum is a useful additive, isn't that correct?
Yes, and you're right. And we've changed our cell design, we've changed some of our palladium, and I fear that the aluminum that used to help us years ago in a different cell design with a different palladium source is neither good nor bad in our present experiment.
So that suggests that there's some surface, potentially some surface effect that is dependent upon the parameters, for example, maybe current density and something of that sort. I mean, in other words...
I think it's a materials effect. I think the surface of the palladium that we're using now is similar than...
It's similar, but it's just a different set of experimental conditions.
No, I'm sorry, just the opposite. I think it's dissimilar. I think the palladium, from lot to lot, palladium is dissimilar.
So it's just really purely a surface effect?
Yeah, I feel so.
Well, that would make sense. Yeah, okay. I mean, I think it's important to get out these distinctions because people can go away saying, well, I said 1 year aluminum worked and next year it didn't work.
Thanks.
Okay, one more discussion, please.
If you make a plot of what you call surface potential versus concentration as measured by the resistance ratio, what do you observe? What is the shape of that curve?
In this first cell, it pretty much reproduces that recorded by Lewis and Fleming. As it must.
What is the shape of it?
Oh, okay.
Is it a straight line?
No, above 0.9, it's a straight line. Between like 0.9 and 0.96, it's a straight line. But if it goes through 0 near the phase transition around 0.7 and stays there for a long time, and then there's another...
I'm interested in the range from above the phase transition, all in the beta range. What happens with surface potential versus concentration?
It's pretty much a linear straight line.
Straight line?
Yeah.
That's very interesting. Thank you.
Thank you very much, Andrea. Dr. Andrea. Next presentation is number 27. Sustentation of higher between loading ratio in quality. Presented by Tewazawa, Sano, Kamiyama, Oyabe, and Owe. Presenter is Tewazawa, Doctor. Please.
Now, I'm going to talk about our studies on nutrient loading in palladium. We have studied in attempt to provide palladium cathode and to propose electric conditions for the reproducible attainment of excess heat. And we have studied for these objects until ICCF-5. These are our conclusions claimed at the conference. In the previous work, two kinds of palladium surface treatment were found effective to increase the deuterium loading ratio. One is by etching a palladium rod with the aqua regia, and the other is by annealing it under vacuum. After either of these conditioning, a deuterium loading ratio as high as 0.95 was achieved by our standard method of step-up current electrolysis. Therefore, all of this study were carried out with ex-palladium cathodes that could be obtained higher loading ratios. The contents of our presentation are as follows. First, problem. Second, improvement. Then, findings. Next, explanation. And final, conclusion. First of all, I'm going to explain our experimental system. The deuterium loading into palladium was performed by the electrolysis in an open cell. This figure shows the electrolytic cell used in the present loading experiment. The palladium cathode, palladium rods were 2 mm in diameter and 50 mm in length. And the loading ratio was determined by the resistance method, that is, with the use of this calibration curve. This figure shows a typical successful example using an etched palladium rod as a cathode by step-up current electrolysis. These black plots show the change of the resistance ratio, and this red line shows the current density. This scale shows the deuterium loading ratio over 0.75 that are calibrated from this resistance ratio as described previously. The maximum loading ratio attained was about 0.93 at 0.2 ampere per square centimeter. However, as can be seen in this graph, it is often observed that the loaded deuterium starts reloading after reaching the maximum loading ratio under current density. We have not been able to sustain the higher loading ratio for a necessary period of time to come back to observe any excess heat. Recently, our studies have been focused on solving this problem, that is, on maintaining higher loading ratio at a higher current density for a significant period of time. We would like to report about the new techniques to sustain the maximum deuterium loading ratios and the cost of deloading. Why does the palladium cathode start deloading the deuterium after reaching a maximum loading ratio? We have monitored the cell voltages during the electrolysis. A cell voltage is 1 between the anode and the cathode. This figure shows the changes of the cell voltage. As can be seen in this figure, the deuterium loading ratio is observed to associate with the cell voltage. We consider that a cell voltage during the electrolysis is one of the key factors to control such deloading. We have devised and confirmed 2 new techniques to hold the cell voltage constant. These are schematic figures to explain the techniques. One is full constant cell voltage electrolysis. The designed cell voltage is applied at the start of the electrolysis, and the other is the step up and increased current electrolysis. After the maximum loading ratio is attained by our standard method of step up current electrolysis, the cell voltage is kept constant. Accordingly, electric currents increase at a certain rate. In other words, it is a partial constant cell voltage electrolysis. This view graph shows the changes of the resistance ratios with various fixed cell voltages. From these results, the optimal constant cell voltage is observed to locate between 3.0 and 3.2 volts in our experience. This figure shows one of the results with our full constant cell voltage electrolysis. The constant cell voltage is chosen at 3.1 volts. The maximum loading ratio over 0.92 is attained, but the loaded deuterium is observed to decrease gradually, and the electric current density is observed to increase gradually, but still remains below 0.1 ampere per square centimeter. Next, I would like to show the result with the step up and increased current electrolysis, as compared with the result with the step up and constant current electrolysis. This figure shows the result with the conventional step up and constant current electrolysis. At constant current electrolysis, as the cell voltage decreases, the deuterium loading ratio is observed to decrease. And this figure shows one of the results with a step up and increased current electrolysis. This example was carried out with a damped current electrolysis as an increased current electrolysis. When the current is controlled in such a way as to keep the cell voltage constant, about 3.6 volts. As expected, the maximum deuterium loading ratio can be maintained for more than 200 hours. In summary, full constant cell voltage electrolysis is effective but not perfect with regard to deloading. Step up and increased current electrolysis is quite satisfactory. Then the maximum deuterium loading ratio can be maintained for more than 200 hours with a higher current density. Further, we think that electrolytic condition before reaching the constant cell voltage is crucial. Why does the cell voltage decrease under constant current density? Cell voltage is able to be expressed in this equation. We are going to discuss these effects on ohmic drop and deuterium overpotential on cell voltage. In our open cell, the electrolysis always concentrates electrolyte and lowers the cell ohmic resistance. As can be seen in this figure, our cell ohmic resistance is observed to decrease linearly with total electric charge. The amount of ohmic drop decrease was found to be approximately 0.1 volts for the electrolysis with 0.125 ampere per square centimeter for 200 hours. Therefore, the cell voltage drop over 0.5 volts cannot be accounted for only by decrease of ohmic drop. This figure shows the schematic electric cell for measuring the electrode potential on the palladium cathode. RHE for a reference electrode is installed in the cell without any structure change. Ohmic drop between reference electrode and the cathode was measured by the current interruption method. This figure shows the change of the deuterium overpotential against electrolysis time at 0.125 ampere per square centimeter constant current density, followed by step-up current electrolysis. As can be seen in this figure, the overpotential is observed to decrease with electrolysis in spite of the constant current. Then, in this figure, we find an approximately linear relation exists between the cell voltage and the overpotential. Judging from this result, we conclude that the decrease of the cell voltage is mostly due to the decrease of the overpotential. The conclusions to be drawn from these results are as follows. The maximum deuterium loading ratio of the palladium cathode can be maintained for more than a week, with the palladium cathode etched by a gauge by means of increasing electric currents. 2. During a long-term electrolysis, the deuterium overpotential on palladium is observed to decrease. 3. It is confirmed that deuterium overpotential is controlled. not to decrease by our method of increased current electrolysis. 4. Higher deuterium loading ratios are able to be maintained by our method. Thank you for your attention.
Are there any questions or comments?
I would like to ask the present speaker in the previous one that you've been considering factors such as loading, current density, but whether one should also consider the total amount of current that is passed through the cell. The point being, the aim is to get a heat excess burst. Now, in the previous day's talks, we very often heard that the surface of the cathode has a lot of gunk on it. It tends to break up, it tends to have cracks, and your blisters on top would break off and things like that. So it may be that just by passing a large amount of current through the palladium makes it deteriorate with time. And therefore, what we really want to measure is the total amount of current that has passed as a function of time. So could you try plotting sometime the number of heat bursts, excess heat bursts observed as a function of the total amount of current that has passed? I mean, the fact that you find it's necessary to maintain a constant voltage and have to increase the current may just suggest that you have some material forming on the surface of your cathode, and this is increasing the problem.
Any other discussions?
I'm sorry.
Yes.
Your third point, I don't know if I understand. You said it is confirmed that the deuterium overpotential is controlled not to decrease by our method of increased current electrolysis. I'm sorry, I don't understand that statement. Can you explain that statement again? The third point under the conclusion.
Third point, number 3.
Actually, we decide it by referring to the cell voltage, which is modified.
I see the problem. The wording is controlled onto instead of is not controlled. This is the opposite.
Okay, thank you. Now your time is behind about 10 minutes, so stop the discussion. Thank you.
But
welcome back. It was not that sharp, but nevertheless, we'll start the second part of the session with paper number 28, in situ determination of structural changes accompanying the electrochemical absorption of deuterium and palladium using synchrotron Wigler radiation by Hagen, Skelton, Dominguez, Quadric, Nagel from National Research Laboratory, Washington, speaker is Dr. Higgins.
Give them 5 more minutes to come back in. Can you sound the bell? The bell. That's what you got to have.
Is it on? Okay.
They just started clapping and telling people to come back.
Well, let's begin. I'd like to point out this is a collaboration at the Naval Research Laboratory between two groups, Chemistry Division, in which I'm a member, and also Don Dominguez, and the Condensed Matter Radiation and Sciences Division, which the other three are a member. Most of you know Dave Daigle, who's actually the superintendent of that division, so one of the co-authors of this paper. Today I'd like to describe some of our initial results using synchrotron radiation for looking at the structural changes that accompany absorption of deuterium and palladium. Most of you don't need to see much of this slide to understand why we're actually embarking on doing some of these studies, but let's help me go over it a little bit. Number one, of course, all of us recognize that high D loadings in palladium cathodes are required as one of the criteria for obtaining excess heat. The question all of us have been asking and have been posed a number of times in this meeting have been, is there some kind of structural change that accompanies this high loading event, whether it's on the surface or in the interior of the cathode? Given the relatively recent results of Fukai, who in fact has identified, and Michael Kubry alluded to this yesterday, has identified a vacancy ordered phase at very high hydrogen pressures in palladium. By high, I mean 5 gigapascals, and also at high temperature, I might add. Those samples were treated at 800 degrees centigrade, although the vacancy ordered phase was actually stable at room temperature. So the question is, does this vacancy ordered phase, if it does it exist, first of all, in an electrochemical system, and does it have any relevancy? Nobody has identified any tetrahedral phase in any highly loaded types of palladium. Third, the desire to actually perform what I would call a real in situ experiment. Some people have done these type of experiments using plates, where they do electrolysis on one side and do X-ray diffraction on the other. That's not the real situation. We want a circular cathode. We're actually doing electrochemistry all around the cathode, in other words, a real situation, and actually be able to look at those at that cathode. Also, what we'd like to do, and which we're able to do, as I'll demonstrate in a moment, is look at some of the dynamics by having a collimated or aperture beam. This gives us the possibility of looking at different spots on the cathode, and also looking at the edge versus the interior, and also looking up and down the cathode. Now, I'll demonstrate some of the former as we look through the sample. First, let's go over a few experimental details. So one of the key prerequisites for doing this experiment, of course, is that many of the materials have to be transparent to X-ray radiation. In this case, we use a poly. We decided when we embarked on this experiment to do it the simplest way we can. And in fact, it is extremely simple. We started out with a polyethylene cuvette, similar to what one uses in UV vis, centimeters squared, 4.5 centimeters high. The cathode, in this case, is carbonaceous material for transparent, obviously, X-ray radiation, which is why we're using it. As the anode material, we use graphite foil. That also is transparent. In this case, we used as the cathode material a 99.9% purity Johnson Matthey wire. It was not annealed, but it was aqua regia etched for 30 seconds. The palladium wire is centered, and then the resistance wires are attached so we can make resistivity measurements of the electrode as we load it. Electrolyte, 10 molar LiOD. Current densities varied from 10 to 400 milliamps per centimeter squared over a 30-hour period. And you notice the low time periods, and that's sort of a result of having to go to the synchrotron. We don't have infinite time on a synchrotron. There isn't anybody that has infinite time. unfortunately. So we have to do these experiments in a somewhat intelligent fashion and try to get as much as we can in a short period of time. Real quick slide to give you an idea why we go to synchrotron. No surprise is the enhancement in the brightness or intensity that we get. X-ray tubes, approximately 10 to the 8th on this scale. When a dipole bending magnet in an electron storage ring like a synchrotron, we get 5 or 6 orders of magnitude. Go to a Wiggler type magnet arrangement, we get even three orders of magnitude more, and in the 3rd generation synchrotrons, we get incredible enhancements with these undulator type magnets and these 7-Jev advanced photon sources. So there's also another reason why X-ray tubes are fixed energy. At synchrotrons, we have a whole wide band of energy. In fact, it's extremely wide band. It goes from hard X-ray all the way down to a UV radiation, but we're obviously only interested in the hard X-ray region. Some of the experimental details for the X-ray source and data collection. The beam line that we're doing our experiments at is a superconducting Wiggler beam line, X17C, at NSLS at Brookhaven National Laboratory out on Long Island. Beam diameter typically is around 28 micrometers. A diffracted beam is collected at a fixed angle of 2 theta equals 13 degrees. In this experiment, then, what we're actually doing, if you remember Bragg's law, lambda equals 2d sine theta. We're not varying angle in this case. We're actually varying energy, or lambda being inversely proportional to energy. So we in fact vary the energy from, it's listed up here, between photon energies of 5 to 100 keV. You see a schematic of our electrochemical cell and the palladium wire in the center, and the collimated beam is focused at various spots on the cathode, and then the diffracted beam energy is collected and analyzed at the germanium dispersive detector. A complete diffraction spectrum over an energy range from actually what we're collecting from about 20 to 80 keV. We're recorded over 2 minutes as a function of horizontal position on the electrode surface. I'll show you a typical spectrum where channel number needs to be calibrated versus energy, but this is an energy scale, and then you're looking at intensity, and a typical diffraction spectrum I'm sure a lot of you have seen. The peaks describing the various Miller indices describing the various diffraction peaks. And this sort of gives you another configuration with a palladium wire, and we step the beam through the 28 micron diameter beam, focus it first at the edge, and then step it through the palladium wire as we do our electrolysis. And as I stated here, the spectrum recorded at the edge and in 100 micron intervals as we go through. The energy scale was actually calibrated, obviously, with pure palladium before we do any electrolysis, and we know the lattice parameter for the unit cell distance of palladium is 3.8898 angstroms. Then we start our electrolysis, and then we start monitoring diffraction peaks and watch the disappearance of the actual lattice peaks and the new peaks due to the palladium deuterium phases forming. This is actually the calibration channel number versus calculated energy for each one of those diffraction peaks given on that first diffraction spectrum that I showed you. Real quick, a phase diagram. Most of you have seen this for palladium. We're interested at room temperature. The alpha phase, as we know, occurs at about a D, maximizes at about a D over PD ratio of around 0.02, 0.03, something like that. And then we go into this alpha plus beta, it's called miscibility gap, where you have two phases coexisting. They're both the same structure, face-centered cubic, where all the deuterium or the hydrogen is occupying octahedral positions. Then after we reach this phase diagram is actually a little off compared to what we find in electrochemistry. Usually this number is about 0.7 to 0.75. We go into the pure beta, into a pure beta phase. The question is, at these higher H or D over PD loadings, what happens? Are there any other phases that exist? Or are there any that, according to how Fukai has observed in the gas-loaded systems, do these occur in the electrochemical systems? Here's the spectrum. This is a comparison, which is up a little bit further, of data taken from the edge before, which is a solid line, and during the first 2 minutes of electrolysis, and this is at the edge. And you'll notice a series of peaks. You'll see some new peaks occurring here, which is in fact due to formation of the beta phase. The beta phase occurs right away during the electrolysis when we look at the edge. There's also some other dotted lines that are almost buried right underneath the main diffraction peaks of the palladium, but those are shifted just slightly, and those are also due to the alpha phase. And just to show you, that's at the edge. This is at the center of the wire. All the other diffraction lines are attenuated, but we're able to see, in this case, the 422 lines of both the alpha phase and the beta phase, palladium, deuterium, in the center of our 1 millimeter wire. So we're actually obtaining diffraction spectra as a function of distance across that wire. Now, this is a sequence of the palladium 422 diffraction peaks going down the columns, and you see as the alpha phase, you begin initially with the alpha phase and a small beta phase, and then the beta phase begins to slowly grow in, and the alpha phase goes away, and you're left with pure beta phase. And that's at the core, at the center of the wire. And this just gives you an idea of translating the channel number into photon energy. We're looking at a general regime of this is beta phase and alpha phase of about 65 to 70 keV. Now, let's take a look at now. I'm going to present, this is a volume change associated with the formation of these phases. The bottom points are the alpha phase, palladium, deuterium, and this is at the edge, so we're initially, when we start recording our spectra, we're already in the alpha and alpha plus beta miscibility gap. In other words, we have both alpha and beta phase formation. We missed totally just the alpha phase. You notice a couple things that are interesting here. The alpha phase actually peaks in volume, or peaks the lattice parameter for that particular phase, peaks and then drops off, as the beta phase, interestingly enough, is also contracting as the electrolysis time continues. There are also some other interesting points in here where we raise the current density, and we see actual expansion of the lattice when we raise that current density, or I should say expansion of the beta phase as we raise the current density. And there are a couple of points on here that does, but essentially we loaded this thing and it remained in the beta phase for the whole time of the experiment. But now what I want to do is compare the core, or the spectra of the middle of the wire with the edge. And you notice some interesting things. The core loads into the beta phase as you would expect. As we put more and more deuterium in, the lattice expands and the beta phase increases in volume. But at the edge, the actual beta phase is actually decreasing. This is an interesting phenomenon. We're not entirely sure what's happening here, but apparently, one must assume here that in fact the deuterium diffusion is occurring at a faster rate than deuterium absorption at the edge. And whether this is a peculiar artifact, or this is something peculiar to this sample or this current density, we've reproduced it at actually lower current density. I should say the current density here is at 10 milliamps per centimeter squared through this whole loading cycle. Whether it's peculiar to this sample, it'd be wonderful if we had a bunch of these spectra at different current densities to see if this was peculiar to current density and at a bunch of different samples, but unfortunately we don't. We only have it with this type of material and at low current density. But also you notice something interesting. These both intersect at approximately the same point, where the alpha phase is actually going away in the interior of the sample. The alpha phase has already disappeared from the edge. At that point, when the alpha phase disappears from the core of the sample, you get this transition. I won't say it's instantaneous, but it occurs very close to the same point in electrolysis time. You get this transition then to pure beta phase, both on the core and the edge of the sample. Now I want to describe another set of experiments where in that set of experiments we actually did not have resistance wires attached to the sample. In another repeat of that experiment, we had resistance wires, and we were able to, this was essentially the electrolysis profile showing the loading curve, R, the resistance ratio, and the current density. We started out at very low current densities here. Initially 1 milliamp per centimeter squared and work up to 10 milliamps per centimeter squared. This big flat portion here is the problem we often encounter at synchrotrons is that we lost beam, and so we actually maintained the sample at 1 milliamp per centimeter squared while they got the beam back up and we got radiation again. Then we took it through a bunch of cycles of low and high current density here, and then we had another synchrotron had another little problem there, and then into another regime where we did some more cycling at low and high current density. Now I want to focus on this initial low loading area and in this area. I'll show this one more time. That's where we converted our resistance measurements to D over PD ratios. That's no secret to anybody. These are those two regimes. This is again, this is electrolysis time, but happens to be synchrotron ring clock. We just haven't converted it yet. This is channel number. The relative volume of a particular phase increases in this direction. So if you look at the beta phase, we're reproducing that data that I showed you before. This is at the edge. You'll notice the beta phase is actually decreasing in volume again. And the alpha phase is sort of staying, it increases a little bit in volume and then decreases back down like we had seen before. And then this is the center part where we're going through those low and high current cycles where the sample is all in the beta phase. So this reproduces actually the original data that I showed you before. We were interested in calculating the rate of this alpha-beta phase transition. So what we did was set R equal to the intensities of the alpha minus beta versus alpha plus beta. We use this equation and let I equal the intensity of either the alpha or beta phase. And then calculate a family of these curves at various positions. And as we go from the edge to the core of that sample. And as we do that, and pick out if you're at, if R is equal to 1, you're only in the alpha phase, and if R equals minus 1, you're only in the beta phase. What we did was pick out the point here on this family of curves where R equals 0, plotted that out, took the slope, and you get an alpha beta, you get a rate at which this alpha beta transition occurs radially from the edge to the core of approximately 48 nanometers per second. I see my time is up, so I'll go into some observations and conclusions. Utilizing the high brightness of the synchrotron, we've seen it that utilizing the high brightness of the synchrotron light is provided by the Wiggler magnetic field enables us to do in situ measurements on palladium, utilizing a palladium wire, and look at both the interior and the edge and get a feeling for the dynamics of the phase transitions that occur in this material. Unfortunately, in none of those materials were we able to load past the beta phase, so I'm not able, at least at this time, to give you any information on any new phase. But you can see the potential, I think, for this technique in looking at this particular system and gaining information. In the mixed phase region, we see that the beta phase parameter increases at the center with increasing electrolysis time, while the parameter at the edge decreases. They intersect at nearly the same point, at which time the transition to the pure beta phase begins. The transition to pure beta phase also coincides with the disappearance of the alpha phase in the center of the wire. A couple other points, and I think the interesting point is the fact we're able to calculate this alpha beta transition rate at 48 nanometers per second. So with that, I'll conclude my talk. Thank you.
Thank you, Dr. Higgins. Now the paper is open for discussion. Comments.
Well, that was a very interesting talk. One thing I quite missed was the delta V reading. At the end, when you've got the complete transition to pure beta phase, what is the percentage change in the edge or in the volume of the video?
At the edge, when you have the transition?
Well, at the end, I mean, when your experiment's finished, everything's beta phase. How much does it change? I mean, does it go from something like 3.84 to 406 angstroms to the edge? Or
I see what you're after. You're after, sorry, I don't have those numbers right at hand. It's 4 point something.
It's 10, and that seems very lot.
Yeah, I mean, these are our large volume expansions. 10% is not unusual.
And that's percentage.
Yes, that's percent.
Other questions?
Is it possible to use your technique in a gas loading system?
Just a moment, wait for the mic.
Is it possible to use your technique in the gas loading system?
Absolutely.
Thank you.
No reason. The work by, if you look at the Phys Rev letter by Fukai, he's actually doing his experiments, and that's a gas loaded system, and he's doing it at a synchrotron.
Thank you.
Okay, that paper came out exactly at the same time when we started doing these experiments, so fortuitous.
A comment and a question. Some years ago, for reasons which might now be apparent to some members of the audience, we were interested in the hydride formation. And we actually investigated this with a fine focus 1 kilowatt tube and position sensitive detector. And if we go on to, with that technique, we use the French 120 degree detector. You know that one? No. There's a French detector which does 120 degree arcs and do no Rayfeld analysis. You see. The question I have to you is, what is the equivalent of the arc? If you tune the synchron radiation, what arc length is that equivalent to using a position-sensitive detector? Can you do 120 degrees? The equivalent.
I don't have an answer for you.
I will close the discussion by adding a comment. The result that you had of different behavior at the edge and at the center of the line is quite similar to what we in Frascati found and presented in our conference with the X-ray extraction in situ during charging. Also in that case, we could see that the charging was higher at depth of 30 to 40 microns than the surface facing the electrolyte. So
now, was that done on a flat sample on the back side?
It was a flat sample.
But there was only electrolysis on the front side?
There was gas on the other side. But the X-ray was just
glancing angle. Right, glancing angle X-ray.
So it's very interesting that the results are comparing.
Mm-hmm.
Well, thank you again, Dr. Higgins. We get to the next talk, number 29, cold fusion phenomena in modified Fleischmann-Pons electrolysis cell by preparata del giudice Paganese Uglietti Parni Sica. Professor Preparata of the University of Milan will present.
Yes, thank you very much. Yes, this talk, actually, I mean, I have the honor of being in this international conference since the beginning. However, this is the beginning for me also, because this is the first talk I gave at this series of conference on an experimental program that I've been involved in for quite a limited amount of time, and that will explain why the experimental data that I will present today are not very precise and accurate. However, I decided to present them anyhow because they seem to produce indications which, to my mind, are somewhat suggestive and maybe interesting. So, I will introduce this talk by discussing a little bit calorimetry, because in trying to validate some ideas I had recently in getting large amounts of excess heat, I had to sort of deal with the problem of what was the best and the most, at least the most expedient way to analyze this problem. Well, in introducing my talk, I would like to remind you that after almost more than 7 years of cold fusion, we're still struggling with a kind of elusive calorimetry, and I will explain you why I say elusive calorimetry, and even more elusive nuclear physics. Well, yesterday night we heard about exciting and more exciting things about a totally new kind of nuclear physics that seems to be emerging from this kind of analysis. As far as theory is concerned, and this is just to set my, just to have my peace of mind, as I explained in Monte Carlo, I think the basic ideas, at least in principle, for theory are no more a problem. I think the problem is just the cold fusion community doesn't seem to have realized that. So trying to understand, how to validate ideas, how to get calorimetry, I was very happy to find out that Martin, in fact, chose a very seemingly arduous way to calorimetry, but actually, I think it was a very, very wise choice, as many of his choices. What do I mean by isoperiodic calorimetry? Well, let me explain to you a little bit of theory, of course, the vice never goes away. And so you define T as the difference between the T of fluids, suppose a well-mixed calorimetry, calorimetric fluid minus the temperature of the bath. Then the calorimetric equation will have that form. You have this, you have the fluid mass and the constant pressure. Then here you have the power, which is produced in the calorimetry, which is sum of an input power times some positive or negative x, x power, not unknown power. And then there's a dissipation function, which just describes the general structure of the dissipation calorimetry. And I will not make any answers on the dissipation function. However, due to the fact that I don't deal with doer, and I'm dominated by, in my cells, I'm dominated by conductive dissipation, I just write the dissipating function in that form, which I always can, of course. And I say this is convenient because in the conductive regime, A is constant, almost constant, and A is constant, and A, in fact, is a slowly varying function of both T and time. Then one must determine this function in order to get a determination of the excess heat of the power which is developed in the cell, in the calorimeter. Now, usually one tries to do this by calibrating once and for all this function, and in this way one saves a lot of efforts and difficult analysis. The isoperibolic method instead uses periodic heat pulses, so a very well-known characterization. The characterization of these heat pulses are essentially perturbations. This heat pulses must be a small fraction of the input power, and the discontinuity and the periodicity. So this is a very good idea, because then you study the transient of the temperature profile of the calorimeter just when you switch on and when you switch off these heat pulses. Then the calorimetric equation around those points can be written in this way. You can put all the things you don't know about the fluctuations of the perturbations and so on and so forth into a linear term in this calorimetric equation, and then you have a simple solution of the variation of the temperature profile, which is this, which is valid when T is very close to the discontinuity point, when the time is very close to the discontinuity point. Note here that tau is a time constant of the calorimeter, and all this constant here can be fitted in several different ways and easily determined from the sperm. And this is what I show with the two students of mine in this paper, which has just been published in the Journal of Electroanalytical Chemistry a few months ago. Why one does the thing this way? Because in this way, one avoids making a priori assumptions about the behavior of the calorimetric fluid in the presence essentially of what you expect to be new and strange phenomena, such as those of cold fusion. I think this is something to be particularly emphasized. All right, now I will talk about the experimental work, which consists of a couple of campaigns of measurement, which lasted about 3 months each in the last year and this year, 95 and 96. The electrolytic cells, well, which I will show picture, is this way.